Today's experiment is one we haven't done for a while. This is experiment 18, oxidation of an alcohol to a carboxylic acid. The experiment today is using nitric acid, con-nitric, instead of the usual chromium-based oxidizing agents or permanganate, MnO4. So we have to have some special precautions today because we are using concentrated nitric acid. One thing you're going to do is wear gloves. So make sure that you're wearing gloves today because we are working with con-nitric. In Gen Chem, we taught you that nitric acid is a strong acid, one of the 7 strong acids. So make sure that you wear gloves in today's experiment. The 7 strong acids that you should have learned in Gen Chem: HCl, HBr, HI, H2SO4, HNO3, nitric acid, HClO4, perchloric acid, HClO3, chloric acid. Those are the 7 strong acids. The common classical strong acids we use routinely in the laboratory. Of that list of 7, only nitric is an oxidizing acid. It will oxidize other materials. You may have in Gen Chem played with nitric acid. You put a small amount in a beaker in the hood, drop a penny in, and watch all this brown gas come off. That's NO2 gas coming off of the nitric acid because the penny is being oxidized. The copper and the zinc in the penny are becoming copper +2 and zinc +2. They're going into solution to make nitrates, zinc and copper nitrate. The NO2 gas is the reduction product coming off, the NO2 brown gas coming off. So again, nitric acid is an oxidizing acid. It oxidizes things. Because of that, we have to wear gloves in the lab today. We're also going to use syringes. You're going to measure out 4/10 of a mil of alcohol. This is a 1 mil syringe. I want you to pull this up to about 1/2 mil. Then point the needle. Be careful, those are sharp. Point the needle back into the flask and push down to about 4/10 of a mil. Then cap the needle. Or no, you're not cap the needle. You're actually going to put this into your reaction vial. Measure it into the reaction vial. Then cap your needle and put this back for the next person to use. So in each lab, there's only going to be one 1 mil syringe. That's sufficient for all of you to actually measure out the benzyl alcohol. I'm going to put out enough syringes for each person to use their own syringe. This is a 5 mil syringe. You're going to uncap this and very carefully pull up 1.5 mils. You can go a little bit over if you want to, but don't go over too much. But pull up 1.5 mils of concentrated nitric acid. Then you're going to cap this. So put the cap back on the needle. You're going to very carefully transfer this to your hood. So carefully walk back to your hood. Make sure your hand's on the cap and the syringe so it doesn't fall. There's no chance of getting stuck with the needle. When you get back to your hood, you're going to uncap this. There might be a little bit of nitric that comes out, so be very careful about that. You're going to push this through the septum, and then at a rate of about 1/10 of a mil per minute, over 10 minutes, you're going to add the con-nitric. When you're done adding the con-nitric acid to your reaction flask through the septum, you're going to pull the needle out. You're going to cap this. You're going to walk back to the dispensing hood and put this in the container I have for used syringes. I'm actually going to wash these out and reuse these every semester. So we have to wash these carefully to neutralize the acid, then dry them, and then I'll store those in our stockroom in a separate container that'll be used just for this experiment. So after they're thoroughly dry, I'll actually put those away. But make sure these go into that container in the hood and make sure the needle's capped. We don't want any accidental stick or stabbing and have con nitric go into your hand. That's kind of bad. We don't want that to happen. So again, be very careful with con nitric. Make sure you're wearing gloves. If you ever get nitric acid on your skin, it turns your skin yellow because it reacts with aromatic amino acids and proteins and turns those kind of a yellowish color. And it takes about 2 weeks for that to wear off. That's if you just get a small amount of dilute nitric on your hands. Con nitric can cause severe burns. So again, be extremely careful because it's an oxidizing acid. It's somewhat hazardous. It's not too hazardous, but we want to maintain safety in the lab at all times. On that note, you're going to heat your mixture, I believe, for about 20 minutes. And then when you set up your apparatus for today, when you're setting up your apparatus, this is the picture of our apparatus. Notice the drying tube. You can leave the drying tube empty. This is the setup we used to use when we all had to work on the bench. Nowadays, in the new building, we work in a hood, so it's a lot safer. We don't have to catch the gases as they escape. They can actually come out the top and go right out the hood. So you do not have to pack the drying tube. You should, however, point the tube toward the back of the hood so the gases are going away from you and out the hood. That way you don't run the risk of accidentally inhaling something as you're working in the hood underneath the sash. So again, you can leave that empty, but make sure it points toward the back of the hood so the gases escape away from you, not towards you. So after addition is complete, you're going to heat the mixture for 20 more minutes, then cool the vial in an ice bath. You should see very little, if any, NO2 gas, the brownish gas visible in your reaction flask. But you should disassemble all this in the hood anyway. Don't pull this out of the hood quite yet. You're going to collect the crystals by gravity filtration the first time. So collect by gravity filtration using your Hirsch funnel. Do not put filter paper in the first time. Just collect by gravity. That's going to allow us to filter off the benzoic acid crystals to get those away from any remaining nitric acid, any nitric acid residue. Why don't we want to put filter paper in this flask? What's the danger of filtering the con nitric with filter paper? Well, the answer is con nitric will react with the filter paper. Filter paper is cellulose. If cellulose comes in contact with nitric acid, it becomes nitrocellulose. This is actually cotton balls that were soaked in nitric acid, then rinsed and dried. Nitrocellulose is also known as gun cotton. And if you have any nitrocellulose residue that gets in the trash cans or in the sink and dries out, and then for some odd reason there's a spark or something that can set it off, you end up with this situation. Boom. We don't want any spontaneous fires to arise weeks after we've done the experiment and have forgotten that there's actually nitrocellulose residue left over from this experiment. So do not filter the first time with any filter paper because we don't want any dangerous nitrocellulose residue to dry out and then appear someplace where we don't want it and then have it go boom. Okay. It's not so much the fire itself, it's what could catch fire when this stuff ignites that can be a problem. For those of you that don't know, that haven't worked in the lab as long as I have, I was even a lab assistant in high school where I would make up solutions for chemistry and biology, as well as do the experiments all 4 years I was in high school. One thing you learn is never mop up concentrated sulfuric acid with paper towels. because sulfuric acid is a dehydrating acid. It dehydrates the cellulose, it forms carbon, pure carbon black. But the reaction is so exothermic, it gets so hot, it will actually cause the paper towel to ignite. So yes, in my lifetime, I've seen a few times where someone has mopped up concentrated sulfuric acid with a paper towel, thrown it in a waste container full of paper, and then 10 or 15 minutes later, the entire wastebasket catches fire. Okay, that's a very dangerous thing. So do not ever mop up concentrated sulfuric acid with a paper towel. That's why we have sponges in every hood. Wet down the sponge, get it good and wet. You can wipe down the area that the spill has taken place and then rinse that out with lots of water. We have bicarbonate powder you can also put on the hood, the floor of the hood, to neutralize the acid. Mop it up with a sponge and keep those sponges good and wet. Okay. The same with nitric acid. Nitric acid reacts with cellulose to form nitrocellulose. And somewhere down the chain, one of our custodians may be accidentally burned or injured because they emptied a waste container that had paper towels or other cellulose residue that was used to mop up nitric acid. So don't ever mop up nitric acid or sulfuric acid with paper towels. Always use a wet sponge and then rinse out that sponge with lots and lots of water. So again, the second time you're going to filter off the crystals after they've been recrystallized, use filter paper the second time. That way you'll capture the crystals of your benzoic acid. Since we're using 0.4 of a mil of benzyl alcohol, we should only have about half a gram of benzoic acid, about 500 milligrams, roughly, at the most, at the very most. Somewhere in that ballpark. At any rate, don't use a lot of water in the recrystallization step. Benzoic acid is about 0.22 grams per 100 mils soluble cold water, 2.2 grams per 100 mils hot water. You really shouldn't have to use more than 15 or 20 mils of water maximum to recrystallize your crude product during this experiment. In fact, I would go for 15 mils of water and then heat it hot, let it cool. Most of your material should come back out. Now, I do want to go to the whiteboard briefly to talk about some things. So let's go to the whiteboard. And here we are at the whiteboard. So we are in my office using my Wacom tablet and Zoom tower. What we're doing today is typical of lots of transformations. In this case, we're trying to take benzyl alcohol and convert it to benzoic acid. Today's product, we're actually going to recover and recycle. We're going to reuse this in 3010 lab and possibly 3005 lab. So the product you're making today is not going to go to waste. We're actually going to reuse it, recycle it for different experiments. So this is a primary alcohol going to an acid. There's lots of ways we could do this. One is chromic acid or Jones reagent, which is made by taking potassium dichromate, mixing it with sulfuric acid, or chromium trioxide and mixing it with sulfuric acid. At any rate, that will take a primary alcohol all the way. It's pretty harsh conditions, very strong oxidizing conditions. We can also use pyridinium dichromate and convert that to also benzoic acid. What else can we do? We can take Potassium permanganate, one of my favorites. Permanganate's purple. This is going to oxidize the alcohol. This is going to go to Mn plus 4. So in this reaction, Mn plus 7 goes to Mn plus 4, manganese dioxide. In the above reactions, chromium plus 6 goes to chromium plus 3. So the metals are reduced as the alcohol is oxidized to the acid. Chromium and manganese are problematic for the environment. We don't really want to do things with chromium much anymore. Chromium plus 6 is a suspected carcinogen. Of course, being a heavy metal, they are damaging to aquatic life if we get this in the wastewater. Likewise, manganese can also have some problems with aquatic life. So we really don't want to generate a lot of waste involving chromium and manganese anymore. Today we're using nitric acid, and we're going to generate, again, benzoic acid. And the byproduct here is NO2 gas, the brown gas that comes off. If you put NO2 gas into a syringe and cap the end off and then increase the pressure, you can have an equilibrium reaction where this goes to colorless N2O4. And then as you release the pressure, it goes brown again. I used to do in Gen Chem quizzes Beavis and Butthead problems, where Beavis would always generate a brown gas and Butthead would remind him about the equilibrium. But I digress. That's a topic for another time. This is benzyl alcohol. This is the exact same equation that's in your lab manual. For the chemically challenged or the chemically impaired, I want to point out that this equation is not balanced. It's not balanced really for mass or electrons. The first thing we need to do is balance electrons lost and gained. We do that by assigning oxidation states to everything. So let's assign oxidation numbers to things. In the alcohol, we don't count carbon groups attached to the carbon. Those come to 0. Each of the two hydrogens is +1, so that's +2. The OH is -1. So we have a +1. That means this carbon has to be -1 because the sum of all the formal charges over the oxidation states has to equal 0. Here's nitric acid. Oxygen is always -2 unless it's in peroxide, which is -1. -2 times 3 is a -6, +1 for the hydrogen, that makes that +5. Here we have a +3 carbon for the acid. And here we have a +4 for the NO2. We couple together like atoms undergoing change in oxidation number. So to go from +5 to +4, you have to gain 1 electron. Gain of electrons is reduction, and that makes perfect sense. Because nitric acid is the oxidizing agent, it's being reduced. The alcohol is going from -1 to +3, so that is a loss of 4 electrons. Loss of electrons is oxidation. We can also tell we're being oxidized because it's gaining oxygen. Gain of oxygen is also oxidation. But we have to balance electrons lost and gained. This is losing 4 electrons, it's gaining 1. We multiply this side by 4 to balance electrons lost and gained. That means we put a 4 in front of the nitric acid, a 4 in front of NO2. So electrons lost is equal to electrons gained. Now we have to balance mass. Since there's no charges in this equation, we simply balance the mass by using water. On this side, 4 times 3 is 12, plus 1 is 13 oxygen. On the right side, 4 times 2 is 8, and 2 is 10 oxygen. We're going to add 3 waters. We add 3 waters, so that's 13 oxygen. 13 oxygen. How many hydrogens do you see? 3 times 2 is 6, and 1 is 7. 4, 5, 6, 7. So the mass should balance on both sides. If the charges balance, there's no charges in this equation. Electrons lost equals electrons gained, so electrons balance, charge balances, and mass balances. We know we're done. So this is a balanced equation. So the stoichiometry is obviously not 1-to-1. It takes 4. It takes 4 nitric acids for every 1 benzyl alcohol to generate benzoic acid. Now, I like to balance things by the whole reaction method. The lab experiment and the lab manual wants you to write the half reactions for the reaction, the overall process. So I'm going to leave that to you to break this apart into the half reactions for your pre-lab, for the pre-lab part of today's experiment. This reaction should be straightforward. Again, I want to caution you, the faculty and the TAs will be walking around making sure that you're extremely careful handling nitric acid via syringe. We don't want any accidents in lab today or this week. So that should take care of what you need to know as far as the lab experiment goes. It should be very straightforward. Again, don't add the nitric acid too fast. That's the one thing that could cause a lot of problems. It can run away from you. So make sure you don't add too fast. When your syringe is in the flask and you're at the 1.5 mil mark, just over a period of 10 minutes, just like waiting for the ball to drop on Times Square. For 10 minutes, just pace yourself and add, especially in the beginning, because initially it's going to be very reactive, very vigorous reaction. You do not want that reaction to run away from you, because it could pop up the flask, it could spray nitric acid all over the place, which also means that you better be wearing safety goggles. Be sure you're wearing goggles and gloves for this experiment as we work in the lab this week. So that's the main things that are of concern as far as safety and the general gist of the reaction. It's actually extremely straightforward and very easy as far as the reaction process goes. Again, I can't stress enough, just pay attention, be extremely careful with the nitric acid, wear gloves, and add slowly. When it says add over 10 minutes, that means add over 10 minutes, very slowly, especially with the initial additions, because you'll see it's very vigorous. It's a very vigorous reaction. So, I enjoy lab. I hope you guys enjoy lab as much as I do. I know the rest of the faculty enjoy having you in lab. Stay safe. Take notes for the pre-lab lecture quiz. And we'll see you again next week via video. Okay.